there a volume or?
It's on. It's on.
Okay. I will speak down. Welcome, everyone. We are so delighted to be able to share with you the first ever pictures of a black hole. Yeah. Now, taking these pictures required creating a new instrument. This instrument took decades to develop and involved hundreds of people, many of whom are part of our local group here at the Center for Astrophysics. So today you're going to hear from a panel of experts. We're going to walk you through the results, how we got them, what they mean, and then we're going to open it up and you can ask us any questions you want. Now, to put things in context, if you go out and look at the night sky, tucked in between two constellations, Virgo and Leo, is a giant elliptical galaxy called M87. Now, this galaxy is actually enormous, but it's 55 million light years away. And because it's so far away that even the best optical telescopes can only see a ball of stars in the sky with a faint jet protruding from it. So that's what you see with the Hubble Space Telescope. We can peer more deeply with radio telescopes, and there you see a jet takes over. And at higher and higher frequencies, the jet becomes translucent, and you can look down through it until you get all the way to the heart at the image that we were able to produce with the Event Horizon Telescope. Now, sitting at the heart of this image is a black hole that is an absolute monster. This thing is 7 billion times as massive as the sun. Now, we have lots of ways of inferring that there are black holes in astronomy without ever being able to take a picture of one. And among all the different methods we have, this is still one of the biggest black holes that has ever been seen in the universe. It's huge. The event horizon of this black hole would actually envelop the solar system. It would extend beyond the orbit of Pluto. And yet, because this is so far away, it is still microscopically small in the sky. The size of this black hole is about the same as a donut sitting on the moon, or an atom held at arm's length. And so that's why we had to create this new type of telescope to be able to see it. Now, black holes have been predicted for over 100 years since the birth of general relativity, Einstein's theory. But no one's ever seen a picture of one until now. And what that allows us to do is test general relativity in entirely new ways. So to understand that, you have to understand that near a black hole, the gravity is so strong that even light is bent. So here are photons moving near a black hole. And if they go close to the black hole, they can actually be whipped around by the strong gravity of it. And so if a black hole is sitting in a bath of hot plasma that's glowing, there are photons flying everywhere. The ones that come too close to the black hole fall into the black hole. The ones that come near it are whipped around and bent, and the ones that are far away come mostly straight towards us. And the net effect is that the black hole casts a shadow on that background bright emission. And this shadow is expected to be nearly circular. So this is a test of Einstein's theory that we can do now with an image, and so we'll discuss that later today and what it means. Now, to build this instrument, what we had to do is actually join telescopes that are spaced all over the globe. So the Event Horizon Telescope is not one telescope, it's many telescopes all working together, being processed after the fact using computational astronomy. And we use a technique called radio interferometry. And this technique is a little bit different than optical techniques. And the difference is that in optical techniques, you just produce an image directly. But in interferometry, you get this incredible angular resolution. But instead of producing an image directly, each pair of telescopes just gives you one measurement. So you can see all these different lines joining pairs of telescopes, and each one, called a baseline, samples one spatial frequency of your image. So this is sampling the Fourier transform of the image. And it's providing just one little piece of the whole picture for you. And we have to take all these pieces and turn them together into a single image of a black hole. Now, the challenge here is that we're trying to take a picture of something no one has ever seen using an instrument that no one has ever used. And what we have to do is be extremely careful at every step along the way that we're not doing anything that might fool us into seeing a ring on the sky when actually there's something else. And so we're going to hear about every step in that process and all the tests that we did to make sure that this instrument was really working as we expected. So first off, we're going to hear about building the Event Horizon Telescope. And we're going to hear this from Jonathan Weintraub. Jonathan is an SMA engineer. He's been with the project since the very beginning, and he's one of the co-leads of the instrument working group. Next up, we're going to hear about this incredible challenge of doing the EHT data processing. And we're going to hear from Lindy Blackburn and Machoke Viel. Now, Lindy actually led the data processing team. He's currently a radio astronomer at the Center for Astrophysics. And Machoke is a postdoctoral fellow at the Black Hole Initiative up the street. And he led all of the validation tests that we did on the data. After that, we're going to hear this beautiful story of how we were able to make an image from the data. And this involved many, many different people. And Katie Bowman and Daniel Palumbo are going to tell us about the steps that we did to make that possible. So Katie is a postdoctoral fellow at the Center for Astrophysics, and she'll be starting as Caltech faculty soon. And Daniel Palumbo is a Harvard graduate student. Following that, we're going to hear from Dom Pesci. Dom is a postdoctoral fellow at the Harvard Black Hole Initiative, and he was part of the modeling group that took these images and the data, and they used them to estimate what the properties of this black hole were, what the mass of the black hole is, and the properties of the shadow. And he pioneered a lot of the techniques that we used there. And last, we're going to hear from Andrew Shale. And Andrew is a Harvard graduate student who's just about to finish and start as a postdoctoral fellow at Princeton. Andrew just won the Keto Award for excellence in theoretical work here at Harvard. And he's done extraordinary efforts to really interpret these images and tell us what they mean both for astronomy and physics. So it's an incredible team that we have here. I hope you enjoy hearing from them. And with that, I'll hand it off to Jonathan.
I guess everyone can hear me. I don't quite know how to drive this computer. That's funny, I'm the instrument guy. It just doesn't have buttons that look like mine. Thank you much. That was Machoke Viel, and thank you. Thanks very much to Michael Johnson. So Michael introduced the concept of VLBI, right? And you've got telescopes on the globe, and they're on different continents, and they're separated by a long baseline, and that's absolutely key because diffraction tells us that the further away we put the telescopes, the narrower beam that we can form. From an instrument perspective, there's a variety of challenges to this. One is that we don't have physical connections to all the telescopes. So to maintain coherence, we need atomic clocks that are accurate to a part in 10 to the 14 or a part in 10 to the 15, 1 second in 10 million years. And actually, the hydrogen maser time standards that we use were invented right here in the Harvard Physics Department by Norman Ramsey and Daniel Kleppner. Kleppner is still at MIT, I believe. The other thing is that you can see there's a time delay between the arrival time at the top telescope. The signal arrives a little bit later relative to the bottom telescope, and also the Earth is rotating. Now, the Earth rotating changes the array under the source, and is very crucial to our imaging process, as you'll hear, but it also introduces Doppler shifts, and both the delays and the Doppler shifts are changing all the time. We have to track those. So I want to offer a little bit of personal history because my association with the EHT goes back to 2006, and I got involved in some of the very early experiments. And this was one where we only had 3 baselines. We had a station on Hawaii, the JCMT, we had one in Arizona, and one in California. This tiny array, what it did do is it worked for the very first time. It actually worked on Sagittarius A star, the galactic center supermassive black hole. We also got good data on M87, but the Sag A star result illustrates something that has kind of driven the instrument development subsequently. And you'll notice kind of a Gaussian on this plot up there. And that Gaussian is sort of the simplest fit that you can do to the very small amount of data that we got. There's the abscissa is the length of the baseline in wavelengths, okay, times 10 to the 6. So the 1,000 is a billion wavelengths along the baseline. And we got a whole lot of detections from Arizona to California, which was 600 kilometers. And that had actually been done before on the Galactic Center in Europe between Spain and France. But then we get a big cluster of about a dozen or 15 detections from Arizona to California, and only 4 from Arizona to Hawaii. We had all the scans from Arizona to Hawaii, but the signal-to-noise ratio wasn't sufficient to make a detection. And we got no detections whatsoever from California to Hawaii. We just got an upper limit. But we knew California was working because of the short baseline detections. So really what we needed was sensitivity improvement. We were able to extract a size for what we were seeing of 37 microarc seconds, and that size is event horizon scale. I'm just going to note that there's a dotted line there, and the dotted line has a bounce in it. And you'll see that bounce again in some of the later presentations. It also fits the data, is the point. We had so little data that you could fit many models to it. I've been involved in engineering projects, and I only give a rough overview, but they've been engineering projects directed towards improving the sensitivity of the array. So one of the projects I was involved in was phasing up the submillimeter array. And you'll notice that the submillimeter array is a telescope on Mauna Kea in Hawaii. We also did experiments with the JCMT. In fact, the very first fringe I just showed you was gotten with the JCMT and the CSO. Those are single-dish telescopes. But the SMA is an array, a local array on Mauna Kea, and in order to get the maximum sensitivity out of it, we had to form a sum with a phased array of all the dishes in the submillimeter array so that it just looked like one dish that we could consider to be a single EHT station. So I worked on that project, and subsequent to that, another team of people went off to the much bigger radio telescope in Chile called ALMA, the Atacama Large Millimeter Submillimeter Array. And a colleague, Jeff Crew, is right here in the audience as well. And they phased up ALMA. And ALMA is, SMA is really a pathfinder to ALMA. ALMA is so much bigger. It has about 60 dishes, and they're 12 meters in diameter, as opposed to SMA, 6-meter dishes, and only 8 of them. When ALMA came online in a phased mode, that really transformed things in a manner that you'll hear. I've got to keep moving here. The other way in which we enhanced the array was, the sensitivity was through additional bandwidth. And you can see this is expressed in recording rate. And you can see we were at a bandwidth of about 4 gigasamples per second from 2007 to 2015. And then things just took off asymptotically to 64 gigabits per second. We did this with hardware. Those are 5 gigasample per second A to D converters, a field programmable gate array for processing, and 8 10 gigabit per second Ethernet ports on the back. In future instrumentation, we'll be using 100 gigabit per second Ethernet. And we deployed these racks of equipment to stations all over the world, single-dish stations, with block-down converters, A to D converters, and you can see the lower part of the rack are the data recorders without the disks in them. We start with by taking samples. We start with an RF signal, we down-convert it to an IF signal, we take 2-bit samples to record, and we record the samples on the disk packs that have to be shipped to a central location for correlation. And this is the correlator. Jeff is in the middle there, and colleagues Kazu and Vincent. Kazu will also be presenting, will also be on the panel today. Standing in front of a software cluster that basically does the integrating of the data from all the stations. There's one at Haystack Observatory here in Massachusetts, another one in Bonn. And this shows then, in 2007, we got a long baseline detection, a one short baseline detection. And this shows that red triangle there, which is that tiny array. The other thing we had to do was make the array bigger so that it would be truly an imaging array, add more stations, get more baselines, sample more spatial frequencies. And that shows the 2017 array. And I'm just going to put one future-looking slide in to close. We want to now put a station into space. And this has many benefits. Longer baselines, baselines that change with a high time cadence and get us a lot of spatial frequencies in a short amount of time. And basically what this result has shown is that there's an enormous amount of work to be done. So if you have the skills, you should get in touch. We'd be happy to talk to you. I'm gonna hand off to Lindy Blackburn now. Thanks very much.
All right, thank you, Jono. So I'm Lindy Blackburn. I'm at the, I guess I have to do this too, Center for Astrophysics. I've been leading some of the calibration and data reduction efforts. As Jono mentioned, we've been exponentially increasing the bandwidth of the EHT for a while now, and one of the consequences of that is that the amount of data we record is growing accordingly. So you might have heard that the EHT records lots and lots of data. We have a few petabytes from these 2017 observations. That means there's a lot of processing involved in that data reduction. You also heard the correlators that were mentioned. That's by far the biggest amount of data throughput. That's when these petabytes of data are translated into about a terabyte's worth of correlations between telescopes. But through and through, we have about 12 orders of magnitude in data reduction. The final image we produce fits in about a kilobyte's worth of information. That could potentially be tweeted, while the petabytes up there fits on trucks of hard drives weighing about half a ton. So it's a large process of data. Here's a movie which sort of illustrates the end-to-end data pipeline. So we see a signal coming in and hitting all the telescopes at once. We have to record them all simultaneously, 1,000 hard drives spinning up at the same time. We fly those hard drives to the correlation centers where they're played back. So they're played back on the same thing, and the virtual mirror here is formed representing the focus of our computational telescope. We calibrate the data. We have to extract those signals, measure them, characterize them, put them on a physical scale, and fit out lots of systematics, so things that in the environment, things that describe the instrument that we care about, but not as far as actually describing the black hole. And then finally, we can form the resultant image. Okay, so this is another diagram of the telescopes. And this is what happens at the two correlation centers, one at Haystack Observatory, one at Max Planck in Bonn, Germany. So the signal's coming in. I represented it hitting one telescope here as a sky signal. And then the correlator forms this virtual telescope by aligning all those signals in time using known Earth delays from a very carefully tuned Earth model, and then forms all the pairwise correlations. So you take of order n antennas and form order n squared measurements out of them from the correlations. And this is in principle a simple problem. So the correlation coefficient, this is my one equation, but it can be found on Wikipedia. So it's very simple. It's multiplying the signals together, averaging that down, maybe normalizing by the strength of those signals. But the problem for us is that the amount of correlated signal is quite small. So for a point source signal, that source is giving identical signals to all the telescopes, but we have a lot of noise in our system. So the atmosphere is radiating and causing 10,000 times more noise than signal power in our data. So we have to average billions of samples to get something out of that, and that's why we take so much data, so we can average it down and extract those weak signals. Another complication is that our signals aren't pure when they come in. They're influenced by things like atmospheric turbulence, and that attenuates the signal and makes it weaker by some amount. We don't necessarily have a good handle on that in the very beginning, and it also distorts the timing of that signal in ways that need to be measured and corrected. So that's one of our major issues of calibrating the data after it has been correlated, is fitting out all of these features from the atmosphere and the instrument. This is one example. So what you see here on the x-axis is time. This is over the course of one of our scans. It's about a few minutes of time. And on the red is the way the atmosphere is delaying the signal in kind of a stochastic random way. And we can't really average down the data until we've solved for this. And it needs to be solved self-consistently throughout the entire array. So this is possible. Our actual signal is for the most part stable. So we use ALMA, which is our very sensitive array in the center of the EHT, to phase stabilize the entire array, lock all the clocks together after the fact, and then we can average the data down stably. This is the EHT 2017 data is unique. As Jonathan pointed out, we built a lot of that array for the first time. The data had a much different nature to it than previous years, and we wanted to be very careful in our processing of it. So in addition to having the two correlation centers, we had three parallel pipelines for calibration and data reduction. This is represented here. I won't describe all the little boxes, but in these three panels, we're building out that systematics model as we calibrate the data and average it down. And then what we can do with those three different pipelines is cross-compare the output from them. So this is represented here, and these nice Gaussian curves mean that our data are self-consistent to within our measurement errors. So this is what we're shooting for. We want to make sure that each of our independent ways of looking at the data, we can also split it up in frequency or in polarization. So each of these ways gives us the same result, so that gives us some more confidence in our final values. And then finally, this is another very important step in the calibration process. When we correlate signals between telescopes, we get the strength of the signal and the phase of that signal, the time difference between signals. But in particular, the strength of those signals is in units of noise in those telescopes. That's the only thing we can measure really precisely is the amount of noise in the signal. But to relate that to a physical unit, like physically correlated flux density from the source, we need to know the sensitivity of all the telescopes. And this is a difficult process for a big array with lots of different instruments like the EHT. It's performed by a couple of grad students primarily at Radboud University here. So after all of this, we have our processed and correlated data. And to describe some of that data, I'll pass it along to Machoke Viel, my colleague at the Black Hole Initiative at Harvard.
Thank you, Lindy. So I'm Machoke Viel. Not only I've been dealing with the data consistency, I'm also the only person who figured out how to operate my laptop. So I'm very proud. Okay, so the way our measurement works, as Jonathan hinted at, we actually rely on the fact that Earth is rotating and we needed to synthesize the aperture, meaning to gather sufficient number of measurements in different locations of different spatial frequencies. So this is what Earth does. If Earth was flat, that would never work. And as the Earth rotates, we are filling in the middle panel, which shows the location in UV plane, in Fourier plane, where we are actually sampling. And the last panel is showing you the amplitude of the complex measurement that we are making. So it's just the amplitude. We also have phases, but amplitudes are kind of nice. They are quite intuitive for people who are a little into that. So when you do that for a couple of years, you actually work out Fourier transform in your head. And if you see something like that, you immediately know something about that. This looks very much like a Fourier transform of a ring. So if you fit a very simple, symmetric, no difference in angle, you just fit a uniform ring to it. That's what you get. So you see, actually, in this moment, we got super excited. That was May 2018, because we saw that something is going on, that maybe this is not just a fuzzy blob that we are looking at. To our amazement, there was more to it. We also saw that independently, on 4 different nights, we recovered the very similar pattern. So this pattern indicating Fourier transform of the ring. Right, but this is not everything. We also have phase information, and we are using special combinations of our measurements that for certain reasons are more robust against systematic effects, against special kinds of noise. And we are using those quantities like closure phases and closure amplitudes. And those quantities have a special property that in case if our source was symmetric, if it was just a uniform ring, they would necessarily be equal to 0. And what you see here is nothing like 0. You see a couple of different closure phases for different triangles. You see that they are violently non-zero. But you see also very interesting different thing, meaning if you look at first 2 days, which were April 5th and 6th, then 3 nights without observation, and then 2 another nights of observation on April 10th and 11th, you see that they are kind of clustering together. So the plots are consistent for first 2 days, they are consistent for last 2 days, but there is a difference between first pair of days and the second pair of days. So we actually see the variability in the structure of our source. We see that this image of a black hole, the data is indicating that it's actually changing as we observe it. And I will hand the presentation to Katie Bauman, who will tell us much more about that.
Great. So now that we have the data, the question is, how do we make an image from it? So unlike with a camera, the event horizon telescope doesn't capture a picture in pixel space, but it does it instead in frequency space. So if you know what a Fourier transform is, we essentially take measurements from the black hole image's Fourier transform. And if we put telescopes all over the globe, we would sample all the different frequency measurements, all those spatial frequency measurements. However, since we only have telescopes at a few locations, that means we only get a sparse number of measurements. And so it turns out that for every 2 telescopes in the telescope array, we obtain the single measurement of the underlying image's 2D spatial frequency, and that's related to the baseline between the telescopes. And as the Earth is rotating, as others have said, we get new measurements since those baselines change, and we get these elliptical kind of paths in the spatial frequency plane that you're seeing here. And notice, like, we have to get those the fine details of the ring, we have to put our telescopes far apart. But at this point, once we've collected all this data and it's gone through the data processing, we can abstract away all the astrophysics and look at it as simply a mathematical problem. We have this sparse data, and our challenge is to find the image that caused it. And if we were given measurements that covered the entire frequency plane, it would be a trivial problem. In the case of no noise, you would just simply need to apply the inverse Fourier transform. However, because we only have a few samples, it turns out there's an infinite number of possible images that are perfectly consistent with the data that we measure. And on top of that, there's this different, quickly changing atmosphere above each of the telescopes, and that causes our data to be really, really noisy. So both of these things make the problem really hard. So how do we go about actually solving for the image? Well, to do this, we developed 2 classes of imaging algorithms to tackle the problem. The first class of algorithms is based on very standard methods used in radio interferometry for decades, called clean with an iterative self-calibration loop. And this is a traditional method of making images, which is great. It's a huge plus that we can use this standard method because it's vetted in the community. But the disadvantage of it is that because it's sometimes very sensitive, you need a significant amount of guidance from a knowledgeable user oftentimes. And a second approach of a class of methods that we've been developing more recently for this data is rooted in Bayesian-style techniques. And in these methods, we try to find a picture that both fits the data, fits the measurements, and is what we define as being a likely image through some sort of prior or image regularizer. So the disadvantage here is that we have to mathematically define what does a likely image mean. But the big advantage of these methods is that we can naturally incorporate other types of error that we experience in the EHT data. And so both of these methods require that we add some additional information into the problem about what images look like. And that can bias our picture of the black hole. So for instance, we wouldn't want to say that we think a likely image is an image of a ring, and then we'd be surprised that we get an image of the ring. We want to be very careful about this when we're imaging. And so the big question we faced when dealing with M87 data is how do we verify that what we're reconstructing is real? And we tackled this through a 2-step process. In the first step, in order to avoid shared human bias and to assess common features among independent reconstructions, we actually split ourselves into multiple teams. So we split about 40 people who worked on imaging into 4 teams that globally span the Earth. And these 4 teams were not able to talk to each other at all during the imaging process. 2 of these teams focused on those maximum likelihood methods, and the other on the traditional clean and self-calibration approaches. And they worked in isolation, trying to make their best image from the data for 7 weeks. And after 7 weeks, we all gathered here in Cambridge, Massachusetts, and revealed the images to each other. And this is what we saw. So, so it was really amazing, actually. So although each picture looks different. They all had different assumptions that were built into them. But we still got the basic structure from all of them. All had a ring of roughly 40 microarcseconds that was brighter on the bottom than the top. And seeing these images, really the happiest moment I've had in the collaboration. A lot of members have shared similar stories, and it's brought a whole other level of confidence to the results as we found the same structure no matter what method or person reconstructed the data. And so here we are with our real first image of the black hole made by averaging those 4 images from the 4 teams and at the end of that day, and the group of people that really made it possible. So without having done this test and having different people reconstruct with different methods, we would never have achieved the confidence we now have in our results, but we still wanted to make sure we weren't imposing some human bias, so we spent the next couple months trying to break our images. And I'll pass that off to Daniel then to talk about that.
Hi, folks. Can you hear me all right? Good? Excellent. So, this sort of blind imaging approach with lots of different teams is great for reducing, the human effect on imaging, but we wanted to eliminate it to the greatest extent possible. Really, at no point in the process should a human look at an image and say, pretty good, tweet it. So, we wanted to do one step better. So, what we've done is we took all of our imaging pipelines.
Oh, that's important. All right. As opposed to just yelling at you, I suppose I can speak in a normal voice. So what we did is we looked at all of our imaging pipelines, each of which has lots of little choices along the way that an expert user makes when forming their images. And what we did is we fixed all of them or allowed them to vary across a large range and then performed what we consider to be an objective selection of the choices that are made during imaging by training each of our algorithms on a set of synthetic images. A lot of these are sort of boiled down to sort of basic ideas, like where are you allowed to put light in your image, or how smooth or sharp should it be? And we don't need to get into the weeds here, but the broad idea is we take a small set, so a ring, a crescent, a disk, just a pair of blobs on the sky, and we try to teach our algorithms to reconstruct these correctly with no human intervention. We just have a fixed method with different choices of little parameters, and then we make hundreds of thousands of images of each of these and select only the best, only those that reconstruct something very close to what's really there. For example, if we were to do this just on a disk, just a flat sort of blob on the sky, we would generate our synthetic data, feed it to our algorithm, and then select images which were very close to the real thing. And then whatever parameters went into that method for producing that image, we then apply to the real data. And in this case, even though we are teaching our algorithm with a disk, we still reconstruct this brilliantly sharp ring with this dark depression in the center. And our algorithms don't know anything about black holes, they don't know anything about rings. All they're trying to do is their best. And we find exactly this sharp image, which now a lot of you are probably getting pretty familiar with. Now what we really do is train on a set of different structures, so a ring, a crescent, a disk, and the blobs. And we perform the same process. We select parameters which do a good job, on average, of reconstructing what's really there and fitting the data. And we apply that to M87 for each of our methods, and we find our fiducial image. Now, by setting a cutoff and saying, okay, well, any set of parameters that do this good are great. They've done a good job at reconstructing what's really there, and they all fit the data. Those correspond to an ensemble of parameters. And this lets us get an idea of, okay, our data doesn't tell us exactly what's there. Our imaging methods sort of fill in the blanks. Where are we most uncertain? And what we've always found is that this ring is rock solid. It has to be there. These are our fiducial images from all of our methods on all of our days. And what you'll notice is that every day we see the same thing. The ring is there. Now, some of these images are blurrier than others. This is mostly an algorithmic difference. Clean, which is the algorithm that's implemented in diffmap in the top row, ends with a blurring step that blurs the image out to the resolution of the array, whereas the other methods will happily crunch down even sharper. But when we blur these out to the same resolution, these images look nearly identical. And we can average them to get our final image on a particular day. And this is what you've all been seeing. We can apply this method every day, and what we see is no matter what data we're looking at, what pipeline we use, there is a ring, asymmetric towards the south, around a dark depression corresponding to a black hole. Now, Dom is going to say a whole lot more about how we interpret this image and how we interpret the data for measuring properties about that black hole. Dom.
All right, thank you, Daniel. So now that we have an image and we believe that image, it's very robust, it's natural to ask what we can learn from it. And one of the most fundamental properties of the black hole that the image gives us access to is its mass. And measuring black hole masses is a tricky business. Historically, there have been attempts to measure the mass of the black hole in M87, and the results have been rather inconsistent. One approach that used the orbits of stars in the galaxy found a mass that was about a factor of 2 larger than the mass inferred from the orbit of gas in that same galaxy. But both of these measurements relied on material, or the properties of material, that was located much farther out in the galaxy than the event horizon scales that we have access to with the data from the Event Horizon Telescope. And so these measurements, these images, give us a chance to try and reconcile these differences and measure the mass of the black hole in M87. And the way we can do this, or the property that allows us to do this, is the fact that the mass of a black hole is proportional to the size of the shadow that we see in the image. So here's a cartoon illustrating rays of light, right? These individual lines are the trajectories of photons in the space-time around a black hole. And what we see is that sort of no matter where the photons start, the gravity of the black hole bends their trajectories in such a way that the image we end up seeing of the material around the black hole forms a circular ring of light with a dark shadow in the center. That's what we see as the shadow of the black hole. And the mass of the black hole and the size of the shadow are directly proportional to one another. The exact constants out front within the context of general relativity are the ones I have listed up here, but this is not really important for this talk. The critical idea really is that there is this proportionality. These constants we end up actually calibrating to numerical simulations anyway, and the fact that we can measure the diameter from the image or from these data is what allows us to measure the mass of the black hole. So how do we go about measuring that diameter? Well, I've got one of the images up here, and we can look at different points around the ring here and measure the peak, the location of the peak brightness. There's this bottom right plot showing how that changes as you walk around the ring. And we can aggregate each of those measurements, each of those radii up in the top right there. And that histogram has a mean that gives us some knowledge of the diameter of this ring, and a distribution, the spread in that distribution, tells us something about the uncertainty in our measurement. But you remember that the image itself is actually reconstructed from the data. It is not itself the raw data, and we don't need to work directly in the image domain. We can parameterize the ring or the shadow shape in terms of simple geometric shapes, or in terms of transformations of numerical simulations. And we can apply these things as models directly to the data, the visibility data, those Fourier transform samples themselves, and we can measure the diameter that way, and therefore the mass. And in practice, we apply all 3 of these techniques to measure the mass of the black hole in M87. And we find that all 3 give remarkably consistent measurements of about 6.5 billion times the mass of our sun. This is an enormous black hole. Even by supermassive black hole standards, this thing's a real whopper. But furthermore, it actually agrees. The measurement we get is really in excellent agreement with the mass inferred from the orbits of stars, much farther out in the galaxy. And so in addition to being the first time we've measured the mass of a black hole using light bending in this way, this is also telling us that we really have a good understanding of gravity across spatial scales that differ by 3 to 4 orders of magnitude. So really an excellent test of how well we know that. And so here I'm just going to compare that, put a little bit of perspective on. This is a diagram that many of you may have seen before, showing the masses of stellar mass black holes. Many of them discovered by the LIGO Observatory, some of them electromagnetically discovered. And if we were to put the mass, or rather the black hole in M87 on this plot to scale, it would be about a mile across. So we shrunk it down a little bit, and we imposed a logarithmic scale on here so that you can actually put it on the screen. But it's big, and then here is where it lives in that shadow that we're all getting so familiar with. And then, of course, I had to throw up the XKCD cartoon to give you a little bit more familiarity. But otherwise, with that, I'm going to end here, and I'll pass this off to Andrew Schell, who'll talk about theoretical interpretations. Is it on? On? OK, great. So now that we've discussed extensively how the EHT collects data, how it calibrates that data, how it uses that data to create images, and how we can measure things like the black hole mass from the data, I'm just going to spend a few minutes at the end here talking about what we think we know now and what we think we've known from a long time about the environment around this black hole in M87. And so what you're seeing here on the left-hand panel is one of those EHT images, this one from April 6th. The middle panel is one of our best simulations. This is what we the best guess what we think this black hole might look like on this day if we had infinite resolution. And so you can see if we had infinite resolution, if we could see with a perfect telescope, we would have a really razor-sharp ring. The EHT blurs it out. So the right image shows the simulation in the middle that is blurred to the same resolution as the EHT sees. So we expect, so those two are in really excellent agreement. But what is this GRMHD simulation in the middle? And how do we construct it? How do we connect it to observations? So to understand that, we have to go a little bit into the physical environment of M87, what we think this world outside the black hole is like. And so what we think is going on right outside the black hole is that there's this thick accretion disk of gas that is swirling in to the black hole. It's very tenuous, not very dense, and it's extremely, extremely hot. So it is tens to hundreds of billions of degrees Kelvin. And it's threaded by these strong and turbulent magnetic fields that are enabling gas to fall onto the black hole, and they're launching this powerful jet. And so as the magnetic fields fall onto the black hole, we think that this process called the Blandford-Zanaik process may be occurring where actually the spin of the black hole, the angular momentum of the black hole that is dragging material around it in space, is actually powering, using magnetic fields to mediate, is powering this jet that we see at all these other wavelengths and images going back 100 years now. 100 years ago was the first time anyone saw a jet from this galaxy, and now we finally made it to the very core where it originates. So the best tools we have to understand this environment are these supercomputer simulations, which evolve the equations of general relativistic magnetohydrodynamics, which is a very fancy word to say. And this is basically solving for a fluid and for a magnetic field in the space-time of the black hole. It's basically, it takes about multiple weeks on a supercomputer to run one of these simulations to see how the gas is moving, how it's orbiting, how it's being ejected. And then we take these simulations and we create images and movies from them using relativistic ray tracing. So we're shooting light through the space-time of the black hole. It's bending around trajectories that we saw earlier in one of these animations. We're adding up the light that's emitted and looking what an observer would see at infinity. And as part of the EHT project, we assembled the largest library of these simulations ever put together. So like I said, each of these simulations takes weeks to run on a supercomputer, and we put together 43 of them, which is the largest collection ever assembled. They span a wide range of parameter space, but two important ones to keep in mind are the black hole spin. So this is the angular momentum of the black hole, how the black hole itself is dragging material with it as the material gets closer to the black hole event horizon, it can't fall straight in. It has to move with the black hole. And then also the magnetic field strength. So there are sort of two states here where if the magnetic field is weak, it can be very turbulent, but if the magnetic field is strong and ordered, it will pile up on the black hole and prevent stuff from falling in and then shoot off this immensely powerful jet. So with these 43 simulations, we can actually construct thousands and thousands of movies. We constructed about 60,000 individual snapshots by varying other parameters on these simulations, like the inclination angle, how are we viewing the black hole. We know that the jet at M87 is pointed basically directly at us, but we can vary that a little bit and see the differences that we get. Once we do that, we want to then fit these images to data. We want to see, we were really excited, what can we learn about these simulations and about the environment around M87 by comparing it to the EHT? And so we took all these simulation snapshots we had assembled, we started fitting them to data, we used techniques to sort of get a sense of what the average simulation might be. But then one thing we found was that actually, when we allowed a few other parameters to fit, only a very few simulations were rejected. So almost all of these simulations could explain the EHT image. And this is sort of for a simple and profound reason, and that the EHT image is dominated by this photon ring. It's dominated by the light bending. So what's happening in the
astrophysics around the black hole doesn't really matter in determining what the image that we see is. The gas can be different temperatures, the gas can have different levels of magnetic field. It's only the geometry of space-time itself that is forming this beautiful ring that we then see in the EHT image. And so we can then fit with 2 different independent pipelines, and we saw the same mass come out of these simulations as Dom just mentioned, which agrees perfectly or really well with the measurement from stellar dynamics. But being astrophysicists, we want to get a little bit more out of the simulation library and learn a little bit more about what simulations we can accept or reject. And so we applied several additional model constraints on these simulations, but one of them is that M87, as we know, produces this huge jet out way past the galaxy. And we've now traced this jet all the way in right to the launch point where we see the lens photon ring of a black hole. And we know this jet has enormous power, and our simulation should produce a jet with the same power. And actually, when we apply that cut, that rejects all of the models in our library that have 0 spin. So we know that the black hole must be spinning. It must be dragging material along with it. If the models are more magnetized, the spin can be lower. If the models aren't that magnetized, the spin has to be really high in order to produce this jet power. And this follows sort of the qualitative prediction of Blanford and Znayak from 1977. And we can actually go into our models and see that in any model that both fits the EHT data and fits the jet that we see in all these other images from going back 100 years, the jet is driven by the extraction of this energy of the black hole itself by these magnetic field lines. And we can do one more thing. We can also determine the sense of orientation of this spin. So if you know the right-hand rule from intro physics class, basically tells you what direction things are moving, and that we know that things on the bottom is brighter. And since the bottom is brighter, that means stuff is moving toward us. This is the Doppler shift of material moving toward us. On the top, it's less bright because the material is moving away from us. So if we apply the right-hand rule, we use the fact that the bottom is coming toward us. We know that the spin must be going into the page, and therefore the spin is moving clockwise on the screen. And so we can reject these alternative models, which would have a counterclockwise spin. So that's sort of the end of our talk. Basically, to wrap up, this is the first image ever created of a supermassive black hole lens photon ring emission around the supermassive black hole being bent by the extremely strong gravity near the event horizon. This was a decades-long project involving the construction of new hardware shipped around the world, coordination with groups all around the world, and the invention of new imaging algorithms, new calibration, and new techniques for theoretical interpretation. And we're just getting started, really, so I think we're ready to take questions now.
OK, so if I could have your attention again, let me just quickly introduce a few of the new faces at the front. We have Jeff Crew joining us from Haystack Observatory. As Jonathan said, Jeff was responsible for helping make ALMA, this anchor for our array, actually part of the telescope. And it was a huge amount of work. And Next up, we have Kazu Akiyama. Kazu and I were co-coordinators of the imaging working group. Kazu's a rock star. He knows everything about everything. And he's just absolutely extraordinary. He's a postdoctoral fellow, a Jansky fellow at MIT Haystack. Next, we have Carrie Hayworth. Carrie is an engineer. She just joined the project. She knows more than all of us about engineering, and so I'm going to direct all questions about that to her. Next is Joseph Farah. Joseph is a little undergraduate phenom who's joined the team and has been absolutely incredible over the last year or so in contributing to so many different projects. Rodrigo Cordova is another undergraduate who worked on the project. So for those of you in the audience who are of that category, you really can step in and do groundbreaking work. And both Joseph and Rodrigo absolutely have. So Rodrigo did lots of the weather modeling. Next is Peter Gallison. Peter is a professor actually of philosophy and history of science and physics and probably more things that I don't know about. But Peter actually did a lot to contribute to how we phrased our entire imaging problem and how we understand how to approach this profoundly difficult problem. So he rolled up his sleeves and jumped into the imaging work and has been a big part of the team. Next is Jim Moran, who more or less invented interferometry, and everything we know about it comes from a book that he wrote that's the Bible of interferometry. So he's done a great job in steering us, and we'll direct all hard questions to him. And last is Alex Raymond. Alex is another postdoctoral fellow. He's working on instrumentation, and he's actually leading some efforts to push our observing it to 345 gigahertz. So this would improve our resolution by about 50%, help us get sharper images, and approach these beautiful images that Andrew showed you. So Alex Raymond. So with that, let me just open up to questions. You know, what are your burning questions about black holes?
Wow, such a big box. All right, so I'm an undergraduate here, and I'm wondering, why did we start with M87 as our first, as our target? And also, are there any other candidates we're thinking about using this technique to analyze?
Let's take that. Okay, so since the birth of the EHT, even from the conception phase, we knew that there were two targets on the sky where the instrument would have about the same angular resolution as the event horizon. So one is M87, and the other is our own black hole in our backyard, Sagittarius A star, at the center of the Milky Way. So Sagittarius star is actually a little better for us. We think it's a little bit bigger, but it has additional challenges that M87 doesn't. So M87 is a monster black hole, which means that timescales are slow. Sagittarius star is actually kind of a small black hole, supermassive black hole, so things evolve very, very fast. A day in the life of M87 is a minute in the life of Sagittarius star. So we saw that M87 is evolving over our 7 or 8 day window. That means Sagittarius star is going to be zipping around even as we're taking data. And so Sagittarius star, we have huge amounts of data on it. It's just a much more difficult problem. That's why we started with M87.
Kind of as a follow-up to his question, is that the same reason that you chose to image a supermassive black hole instead of a stellar mass black hole like within our own galaxy?
So, yeah, so it is essentially the same reason. The only black holes that are large enough for us to resolve with this instrument are supermassive black holes. It's not, you know, the center of our galaxy is not as far as you might think compared to other black holes, which are 1,000 times or 1,000,000 times smaller, right? We don't really know what's out there, but if we're talking about stellar mass black holes at 10 solar masses, they're 1,000 times smaller. And at our distances, we wouldn't be able to see them spatially resolve them like this.
You want me to attempt to, but sorry.
Hi, I just would like to ask if you can help us picture in 3 dimensions where at least a couple of possible rings are. So there is a ring in the sky, which you have taken the picture of, and we've seen some simulations that show how light might be bent by the gravity of the black hole and make this ring. And you've also talked about the spin of the black hole making one side brighter. And then there's also the ring of stuff that's orbiting the black hole and maybe falling into it, the accretion disk. And what I'm trying to picture is whether the disk of material is the same plane as the ring that you see in the sky, or if we know how they are oriented relative to each other.
So the ring that we see in the sky, we would see if we looked at any angle approaching the black hole. So as long as there's enough light filling it, the black hole will bend that light and it will shoot it out toward an observer at any angle, and they'll see a ring. So that's really, the precise shape of that ring will change depending on how you are angled with respect to the spin of the black hole. If you're looking at the black hole edge on, it'll be squished with the spin, whereas if you're looking at it face on, it'll be a perfect circle. So there's no really sense of it being oriented with the plane of the material falling in. We think the material falling in is basically face on to our, the disk is basically face on, so we're looking basically right down at it because we're looking, or at least we're looking straight down onto the jet. Yeah.
So you collect this data on the Fourier plane, right, and then take the Fourier inverse. And then as I understand, you use, there's some kind of guesswork going on what's likely and unlikely pictures you can see. So for example, in these likelihood models. So I was wondering, so is general relativity used in any of these imaging models? And in particular, if yes, then to what extent, and how do you make sure that you test jar versus it being an input?
So the imaging algorithms don't know any physics. They don't know anything about how light travels. They just know sort of data. They just get Fourier components. You could be looking at a picture of a teapot for all we know. The physical analysis of those images is downstream, or side stream, so to speak, in that it can operate directly on the data or on the images we produce. But the imaging algorithms themselves make no assumptions and don't extract any parameters.
So how do you determine what's likely image and what's unlikely image?
So I guess, do you want to say a few words about this?
Sure. So yeah, we don't, at the imaging stage, we don't assume anything about rings or anything like that. But what we do is we define a bunch of different, like it's very unclear of what is a likely image, right? And you don't want to get into the circular argument of saying something is likely and then being surprised you get that out in the end, right? So we define a lot of different functions for what is likely. We say, oh, we want our image to be smooth, or we might have another likelihood function that says, oh, we want it to be, or we call these image regularizers, or we say, oh, we want it to be very sparse, it to be black in most of the image and only bright in certain areas. And then also we have some that are just very obvious, like light is positive. We wouldn't get negative light, right? So we have some that are really based in some physics, but they're not assuming anything about a ring. And we apply each of these different regularizers, different people, different methods, but also different regularizers or different assumptions on what is a likely image. And what we did is compared them all and made sure that we saw that ring in all of them. And basically you have to bend over like crazy backwards to not get that ring a lot of the times, if you have a reasonable kind of regularizing term that defines what is a likely image.
I walked in a little late, so I'm sorry if this was said, but was there anything about black holes that you feel like was revealed through this image, or was there like otherwise one important takeaway that you feel like this image conveyed?
So I actually sort of missed part of that question, so I was hoping somebody else would take it. If you don't have the microphone, you said something, I'm just going to repeat it, and then you.
So I was just wondering if there was anything about black holes you didn't know before that was revealed, or if not, what those
Well, I think, I'm sure that's going to be a question that different people will answer differently, right? What do you personally find the most important? But for me, I think it was, the critical thing was that it really seems to match what we expected almost too well, right? Like it really looks like if you take some of those simulations and you blur them to the angular resolution of the telescope, you find something that, unless you've been staring at the image for as long as we have, you probably can't tell the difference. And it just looks like the same thing. And I think the fact that we didn't, the understanding we have of the astrophysics that goes into simulations and our understanding of gravity seemed to be so good that the image we got was the ring, that was the size we expected it to be, and sort of a distribution of brightness that looks a lot like what we expected it to be, is you sort of learn that you're right? It's kind of like, that's something that I found pretty stunning when I first saw it.
One thought, just to add to that, is I think that as we get used to seeing this image everywhere, it becomes routine in a way. And I think it's important to remember that although we had a lot of evidence pointing to the existence of black holes, we had images that were far from the event horizon, like stars orbiting around what we took to be the black hole. And then we had non-imaging data, like the great work that LIGO had done, that's close up to the black hole. But this is an image that's close up. And that really makes a difference, because images, there's something open-ended about an image. An image can surprise you. An image can reveal something that you don't expect. And it is reassuring that we're able to make models and to theoretically parse what we've understood. But I think the raw ability to be able to see this close to the event horizon of a black hole is astonishing. And what it's doing is a little bit like what Galileo did when he saw the moons of Jupiter. They were important to show the moons of Jupiter. He wanted to show that the glassy spheres of ancient astronomy would be shattered by these moons orbiting around Jupiter. But really what he had was a telescope that could open up the entire field of astronomy. And I think that that's the real significance of what this image says. It says, we can image in the most intense possible gravitational fields in right up to the event horizon. And the open-endedness of that inquiry is really the beginning of a new epoch of inquiry.
Yeah, hi, thank you for that answer, because that was my next question. What else in the universe can have that structure that you constructed out of the Fourier transform? I think that's what was answered. Is there anything in the universe that will have the same image or the structure?
Okay, so it turns out there are, as Peter said, we see these stars zipping around black holes on much larger scales. And so you can produce that same behavior in a lot of different ways. You just need a big concentration of mass, but you don't necessarily have to squeeze it down so much that it turns into a black hole. So the question is, once you squeeze it down so much and we actually get the picture of the black hole, what else could it be? What else could be dark, casting this ring? And so it turns out a number of objects could look like that. A naked singularity could look like that. It might be that there's a huge concentration of mass, but it's not shrouded by an event horizon. And it turns out that would cast a different shadow than what we saw. So we can rule that out, at least for certain classes of naked singularities. Another is maybe it's a wormhole. And that, again, casts a different type of shadow, and we can rule that out. And so we can look at these and then there are other types of exotic objects, and some of them, it turns out, do cast exactly the same shadow as what you would expect for a sort of canonical black hole in GR. So there are these exotic classes of objects that could be consistent with our results, but we're starting to get leverage on, we're able to rule at least some of them out.
Okay, so the next question that I have is, what is the next most important thing that you want to do after the image is formed, apart from all the questions that one can ask? Thank you.
Yeah, so there's a bunch of follow-ups that we are going to do, and they will yield another fascinating discoveries in near future. So one would be the polarimetric images. So what you saw is just total intensity, and light is a vector quantity. It has a direction of the polarization vector. So we will deliver a bunch of results on that. And why is that great? It's great because this will allow us to map the magnetic fields just above the horizon of a black hole. And that could help us, the whole field of astrophysics, to say something more about how those jets are created. That's just one thing. The other thing is everything we're going to do about the Sagittarius A star, about our galactic center. So this one, it's for many reasons, well, it's more difficult to process, but there are many reasons why the science could be even better, because we know quite well mass from the other experiments. We know the distance quite well, and also we expect to see signatures of maybe orbits or maybe some dynamical signatures on timescale of minutes, not days. So it could be that we could actually see some periodicity. That would be amazing, and that would be yet another test of general relativity that no one has really done. Gravity last year just scratched the surface, will go all the way in.
Okay, next question.
Thank you. Well, would that black hole evaporate? And does your information or the picture itself, does that give us any deductional power as to, does that give any estimates on the time decay, if possible?
Jim, you want to take that?
No, I mean, the time for a black hole of this size to decay to evaporate away is 10 to the 70 years. The universe is 10 to the 9 years old, so it's not going away anytime soon.
Sorry, there was a kid in front, and I'll come back up to you guys.
So you've been waiting for a while.
How come in a black hole, the light, you can see light, and in the black hole, light cannot escape out of the black hole?
Joseph?
That's a really good question. So you're right, light can't escape a black hole once it passes the event horizon. And what we're really seeing is we're seeing gas as it's falling into the black hole. It's being sped up to right next to the speed of light, and it throws off all this radiation and as it heats up. And that light, some of it escapes. Some of it can get outside of the strong gravity regime of the black hole, and it can reach our telescope. And so even though we cannot see anything past the shadow or anything past the event horizon, we can see sort of the final cry of infalling matter as it spirals in, never to come out again.
Okay, so what my question is with you guys being one of the greatest teams in astrophysics, how does it feel to be a part of that and with the great accomplishment that you guys did?
Kazu?
Well, so I joined in EHT in 2010 from Japan, and then joined in team in United States. I'm here, Cambridge, in the recent 5 years. Well, I don't know what to say. It's just amazing. So the EHT have a wide diversity. We have a fantastic females like Katie here, and also we have a lot of people who has a huge range of expertise. I myself is a radio astronomer, but for instance, Lindy is come from LIGO, gravitational waves, and then also Katie is coming from computer science. My close colleagues are coming from mathematics, and some people are coming from X-ray astronomy, and all of our people actually who have a wide expertise actually attack on the different and difficult challenges for the EHT. I think this kind of international and also wide diversity in many dimensions actually help making this first images of a black hole.
First off, thank you all for a fantastic accomplishment and the great presentations today. My question is, what steps are you going to take to improve the resolution? Because presumably as the resolution improves, more important, fascinating details will emerge.
Carrie should talk about.
Well, so Jonathan's referring to adding an EHT station in space, which is something Carrie Hayworth in the middle there has experience with. We are wanting to add new sites. One recently added site was led by someone in the audience here, Nimesh, at the Greenland Telescope. It's a part of the EHT array and recently added. And adding more sites lets us fill out that virtual mirror in a better way. Another way that we're looking at improving the resolution of this image is by going to higher frequencies. So you saw these maps showing the baseline measured in wavelengths, and if you shorten the wavelengths, you get more of them between the two stations, and that improves your resolution. Maybe, Carrie, could you talk a little bit about adding a station in space?
Is it on? Is it on? Yeah. Okay. Yeah, I am the engineer. I don't know how to use a microphone. So to add it in space, there's actually several different things we could do. We could put a Leo constellation in. We could put something out in Geo, which is the orbit that actually stops right over one part of Earth. The big thing is actually to be able to sync up with ALMA, which is a big array, to improve the sensitivity. And so what that's going to do is, because on Earth there were several pictures that actually showed the UV plane filling out, and that's, you saw as different sites were reached, you would see that the UV plane kind of goes a little bit at a time. And what we're doing is relying on Earth movement. If we go into space, we don't have to rely on Earth movement anymore. Now we can point where we want, and we're kind of free floating. And so that's a definite improvement in what we have. We also don't have atmosphere to contend with in space.
If I could just jump in there for one part. So fundamentally to the way the EHT works is, the Earth rotates and we sample our image in new ways. And when you can put stuff in space, you're not limited to the rate at which the Earth rotates. And so if we throw things into orbit, which zip around much more quickly, suddenly we're sensitive to a new timescale. As people have mentioned, Sagittarius star is evolving incredibly rapidly. And so it's conceivable that with dishes in space, we suddenly become sensitive to the dynamics at Sagittarius star, capable of forming images in the short windows of time where we might see a feature zip by. So it's not out of this world to imagine, except in the sense that it is literally, that with a space-enabled EHT, we could be making movies of the galactic center and watching it breathe.
Okay,
something to think about.
Last question.
Were you completely certain that you were going to get a picture of a black hole and that it would look like that? Or was there a big possibility that you could see something else? And what did you think that would be?
I think Katie should answer that.
No, we should all be like no together.
No. We could never have known that.
I'd like to address that. I think there was a great deal of luck involved because, as you saw from those jets of material flowing out from M87, there's a lot of stuff in the vicinity that's radiating. That could have been obscuring the ring, but we were just lucky that there was not a dominance of radiation from other processes, and we could see through to that ring very clearly.
Yeah, I wanted to add to that. I've worked on a number of projects over the years which started out with, what if we could? And a long time later, in my case, 10 years on this project, you get to that point where all the hard work pays off. And the lesson here for all of you younger people, since we are at an institution of higher learning, is don't set your sights low. You can do, if you work with the right team of people, you bring together the right skills, there really is no problem that you cannot solve. And I mean that in all seriousness. When I started this, it sounded like a crazy idea, but I'd been after some other crazy ideas, and so I said, this one might work. I didn't know what we'd see, but I figured we'd see something, and that would move the ball forward. So I want to tell each and every one of you to go out, leave this room inspired to go do something else. Get as many of your friends together and solve some problems.
Let me just say, so you can do anything as long as you have good weather.
Okay, so with that, I think we're going to close. I think a number of the panelists can stay. If you have one-on-one questions you want to come up and ask us, and thank you so much. Yeah.